everyone. Today we're going to take a look at implicit differentiation, and I'm probably going to split this into two videos because we are probably going to spend at least 2 days on it in class. I'm going to start out, so there's a definition here for you. If you need to pause the video and write any of this down, please do. But I kind of want to start out with just a explanation of like some notation and then like why are we doing implicit differentiation. So you've done lots of problems like this before, where I give you something like y equals 3x squared, and I say take a derivative. And I don't know that we've ever been real picky about the notation here, but when you're taking a derivative, what you are doing is you are coming here to the left side of this equation and you're saying, hey, I want to take a derivative in terms of x. That's what this means, d over dx, and I think you've seen that in your calculator before. And then you're going to come over here and say, I want to take a derivative here in terms of x as well, okay? Well, on this side, when you do a derivative in terms of x, but you're working with a y, we're not really following derivative rules. We're just rewriting this thing. A derivative of y is just dy dx. But that's what we're looking for, right? We're looking for a derivative in terms of x of a y function. So this thing becomes dy dx. And then over on this other side where I have an expression with just x in it, that's where I'm following my derivative rules. And so I would say this is 6x. And that's my answer. That's what I'm looking for, okay? This is still going to be what we're looking for today. We are looking for dy dx. However, the equations we're going to get handed to us, and I'm going to try really hard not to call them functions because a lot of them are not actually functions. The equations we're going to work with have y's kind of sprinkled throughout them, or they have y's, like if you look down here, I've got a y squared. We have something more complicated than just a lonely y over here on one side of the equation, and that does complicate things a little bit, okay? And so what we're going to have to do, and I'm going to say this kind of in general, but I don't think it's going to make sense until we do the first example, when we're taking a derivative of something that has a y in it, we treat it almost like a chain rule. Okay, so like down here where I see y squared, what I'm really thinking of is, hey, that's a y that we dropped inside of an x function. And so the derivative of y, which is the inside function, is dy dx. And then the derivative of the outside function would be 2y, because I'm following my derivative rules. So let's write out this first one. I'm not going to talk through these steps because I don't think they make sense until you've done a couple of these problems, and then if you come back and reread them, I think they might work for you. But just to kind of put what I was just saying into action, I'm taking a derivative of y squared. We know that when we have something squared, we just bring down the 2 in front, right? But if I'm taking a derivative in terms of y, I also need to apply the chain rule and say the derivative of y by itself is dy dx. So I'm going to say dy dx times, and then I'm going to apply my derivative rule to the outside function, which is the y squared, and I'm going to call this a 2y. And then over on the right side, I'm just going to take a derivative like normal, because that's just an x. So derivative of x is just 1. Okay? I will tell you, if that chain rule piece does not make sense to you, if you don't understand what I'm talking about when I say we're applying the chain rule to the y, all you really need to know is anytime you're taking a derivative of something with a y, it's going to get a dy dx thrown in with the actual derivative. So we're going to find the derivative like we normally would, but we're going to tack on a dy dx. Okay? And again, the reasoning for that is the chain rule, but if that is confusing to you, don't stress about it. Just know to put the dy dx in there. So now my goal is to get dy dx by itself, and so I would come along and say, well, I'm going to divide then by 2y. I'm going to divide by 2y. And so what I end up with is dy dx equals 1 over 2y. And that's it. That's my derivative. Okay? So we're going to have x's and y's kind of in play here, and the dy dx is going to pop up somewhere, and our goal is to get it alone. So let's try it with the next one. X squared plus y squared equals 25. I'm finding a slope, so that's what tells me I have to find a derivative. We'll deal with the specific point in a minute. So I'm going to kind of just move from one side to the other, and I'm going to take all my derivatives. So derivative of x squared, we know that one, that's 2x, plus derivative of y squared. Well, I'm going to start with a dy dx, and then I'm going to multiply that, again because of chain rule, by the derivative rule for y squared, which would make that a 2y. And then equals derivative of 25, that's just a constant, so that's going to equal 0. And now I want to try to get everything moved so that dy dx is by itself. So I'm going to start with this thing that's being added on. I'm going to subtract this from each side. Okay, so now I have dy over dx times 2y equals, over here I have a negative 2x, and then let's divide by the 2y, and I have dy over dx equals negative 2x over 2y. And I could clean that up just a little by canceling out these 2's. So I could just make this so that it's negative x over y. And that's my derivative. This one does want a derivative at a specific point. It wants a derivative at 3, negative 4. So I'm going to say that my derivative taken at the point 3, negative 4 is, I'm just plugging these in for x and y. So the x has a negative on it, so I'm going to make this a negative 3. And that's over my y, which is a negative 4. And then I would say that that's equal to 3/4. And that's my answer. And by the way, there is a way, and I'll try to remember to show you in class if you haven't seen it. We could graph this thing on Desmos. Desmos is really nice for stuff like this because your calculator would not graph this for you. This is a circle, by the way. And we could make a tangent line using this slope and see that this is actually tangent to that circle. But I don't really have a good way to show you when I'm on the document camera, so I'll make sure that we show it in class. Okay, whoops. Next example. And I'm probably going to cut this video off after this example, and then I'll do the other ones in a second video. This one is a little more complex, and this has some things in it that are very common in these types of problems. So try to stay with me. Try not to get too far ahead of me as you're working through this problem. So let's do my derivative. So I'm going to start with x cubed. By the way, I know I'm taking a derivative because I want an equation for a tangent line, which means I need a slope, which means I need a derivative. So x cubed is 3x squared plus, okay, this thing here, 2xy, I have to treat that like a product rule. That's a 2x being multiplied by a y. So I'm going to go off up here and I'm going to say that u is equal to 2x and v is equal to y. So u prime is 2 and v prime is, well, the derivative of y is dy dx. Technically we could say it's dy dx times 1, but we don't really need the 1 there. Okay? So I'm doing u prime v, so that's 2y, plus v prime u, so that's dy dx times 2x. And then one last piece. So both of these came from that middle piece. And then the minus 4y squared. Well, I'm taking a derivative, and it's got a y in it. So I know I'm going to just start out with a dy dx. And then I'm going to multiply by the derivative of 4y squared, following my derivative rules, would be 8y. Equals, and then derivative of 17 is 0. Okay, if you don't understand where any of those pieces came from, I would back the video up right now and rewatch and make sure that you're in a place where you understand where each one of those pieces came from. because now the goal is to do some algebra magic and get these dy dx's isolated. So what I'm going to do first is just kind of divide this thing into teams. There's going to be team dy dx and team no dy dx. So I want to get everything that doesn't have a dy dx moved to the other side. So I'm going to subtract and subtract and subtract and subtract. Okay, gone, gone. And so now I would probably normally do the next two steps together, but I want to make sure that I really emphasize what's happening in the next step. So and then I have negative 3x squared minus 2y over here. Okay, so now in order to be able to isolate this dy dx, what I am actually doing is factoring out a dy dx. I am pulling it out front and then leaving behind the 2x minus 8y. And that's going to allow me to isolate it. So let me show you what I mean by that. I'm going to have to do it down here, but I'm going to take dy dx out and then open a big parenthesis. And so if I've taken the dy dx out, what I have left is a 2x minus 8y. And then that's still equal to negative 3x squared minus 2y. And now to get dy dx by itself, I'm just taking over all my space for this next problem here. Maybe I'll go up here. Sorry, that's obnoxious, but I'm going to divide. So dy over dx equals, and I'm going to have this divided by this. That is going to be a very common thing that happens where you have multiple dy dx's and you just grab everything that has a dy dx, you put one out front, and then you divide by that big parenthesis that's left over, move it to the other side, and you'll have dy dx left over. So this is my derivative, okay? Specifically though, what I'm looking for is the derivative at this point at 3, negative 1. So I'm going to just do at 3, negative 1, but then I'm going to, again, be obnoxious and say I'm going to do the math up here. You follow all my arrows around, right? So I'm going to go negative 3 times 3 squared. I'm just plugging in for x and y. Minus 2 times negative 1 over 2 times 3 minus 8 times negative 1. Okay, that's negative 27 plus 2, so that's negative 25. And then that's 6 plus 8, so that's 14. So my slope is negative 25 over 14, just to cram it in there. And then we still need one more thing. We still need a tangent line. Okay, so let's get to the actual answer here, the tangent line. The good news is I need a point and I need a slope, and I have a point and I have a slope, right? That's what I need, is I need this point and I need this slope. So my tangent line is y minus, now it's minus negative 1, so I'm just going to make it a plus 1, equals negative 25 over 14, and then x minus 3. And that right there in purple, that's my tangent line. Okay, but I had to kind of follow all of that around first to get to the point where I could, really what I needed was that slope there. Okay, so a tip for you, if you were doing a problem like this one and you had access to something like Desmos, I would graph this original function, and on Desmos you can type it in exactly how it's written there, okay? It's going to be some crazy graph. And then type in your tangent line exactly as it's written. And what you should see is at the point 3, negative 1, that line should just barely touch your graph. It should just kind of breeze by like a tangent line does. If it doesn't, then there's something wrong with your equation. But that's kind of the goal. That's what we're looking to find. Okay? Like I said, I'm going to pick up with a second video to do these last two examples. And then you've got some homework to practice with. We're going to spend lots of time on this, and I promise that the more of these you do, the more routine they will start to feel. So don't stress about it. Okay? All right. Have a great night.